discover how these double angle identities come into being. So we are going to start with sine. So by a double angle identity, what does that even mean? It means something like sine of 2 alpha. So it is a double angle because the angle alpha is doubled. Well, what does it mean to double something? I guess maybe I should look at your 2 alpha there. So 2 alpha is our angle measurement. And so doubling means to multiply something by 2, but doubling can also mean to add something to itself. So this would be equal to the sine of alpha plus alpha. So that is the sine of the sum of 2 angles. Well, that's what we worked on last time. So if you look on your formula chart, and we look for the sum, sine of alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta, we have this situation, except this time our 2 angles, alpha and beta, instead of being 2 different angles, alpha and beta, they're both alpha. Right? So we're going to use this sum identity and write this out. So I'm applying the sum identity for sine. So the sum identity for sine says sine of the first angle, alpha, times cosine of the second angle, which is also alpha, plus cosine of the first angle, which is alpha, times sine of the second angle, which is also alpha. Alright, now let's just take a look at this second term. I'm just going to bring the first term down. So, the commutative property for multiplication, right? So over here on the side, right? 2 times 3 is equal to 3 times 2. That's called the commutative property. Whether you know the name of it or not, you've been knowing for many, many years that you can change the order in multiplication and you still get the same answer, right? So we're just going to do this here to show us that cosine alpha sine alpha is the same thing as sine alpha cosine alpha. So that these guys kind of look alike now. And we can say that that is then 2 sine alpha cosine alpha. So I'm going to take my highlighter here. This is my double angle identity for sine. So if I look on my formula chart, double angle, sine 2 theta equals 2 sine theta cosine theta. That's what I got right here. Sine 2 alpha equals 2 sine alpha cosine alpha. So that's my double angle for sine. Alright, so now let's take cosine. This time I'm going to use an x because I kind of don't like writing alphas. So cosine 2x. So again, let's use that idea that doubling something is the same thing as adding that something plus itself, right? And then we want to expand this out using the sum identity. So I'm going to look at my formula chart for cosine. The sum of 2 angles equals cosine of the first, cosine of the second, minus sine of the first, sine of the second. But this time the first and the second angle are actually the same angle. So do you see that it's going to be cosine x minus the sum identity for cosine has a minus in there, sine x, which I can then write as cosine squared x minus sine squared x. So there is my double angle identity for cosine. Well, that's one of them. The cosine, the double angle for cosine, actually has 3 variations. And you can use any of the 3 at any given time, but having the 3 separate variations helps you. So like over here on the side, we just want to remind ourselves about this Pythagorean identity. Our Pythagorean identity says sine squared theta plus cosine squared theta equals 1. Right? We've been using this identity a lot. And some of you are very comfortable with manipulating this identity into its other forms. So you are very used to saying that if I subtract cosine from both sides, sine squared theta equals 1 minus cosine squared theta. Or if I subtract sine squared theta from both sides, cosine squared theta is equal 1 minus sine squared theta. Kind of like fact families back in the first grade, right? If 3 plus 4 equals 7, right? Then 3 equals 7 minus 4, and 4 equals 7 minus 3, right? It's just a manipulation of relationships. Adding and subtracting go together. This is foundational back from first grade, writing fact families. That's all that's going on right here. Alright, so maybe you can kind of see where we can then take this double angle identity and have it have some variations. So let me start with cosine of 2x being equal to cosine squared x minus sine squared x. Right? That's a double angle identity. But what if I leave my cosine squared x the same and I rewrite this minus sine squared with the Pythagorean identity? So I'm going to minus, and now I need parentheses because I'm subtracting a whole quantity. And so right here what I'm doing, I'll use a different color highlighter. That might come out really dark. So I'm taking sine squared x, and I'm doing this Pythagorean identity substitution. Substituting. Here's my dollar bill, you give me 4 quarters. Just trading. 1 minus cosine squared x. Now if I distribute my minus, it's cosine squared x, minus 1 plus cosine squared x. You all follow that? Then I combine these like terms, and I get 2 cosine squared x minus 1. So that's just another version of the double angle identity. And so what did I do here if you're just tracking your steps? I distributed the minus, and then I combined like terms. Alright, so now I'm going to start again with this original version of the double angle identity. And instead of replacing the sine squared, we're going to replace the cosine squared. So I'm starting again here. Alright, and now this time, so I'm going to use a different color highlighter. This time I'm going to take my cosine squared x, and I'm going to substitute with the Pythagorean identity. So cosine squared x goes out, and 1 minus sine squared x comes and takes its place. And then I bring down my minus sine squared x. And then I combine like terms, and that's minus 2 sine squared x. So I did a Pythagorean identity substitution, and then I combined like terms. Alright, and then finally we're going to do our tangent double angle. So if I have the tangent of 2x, right, that's the tangent of x plus x. So I'm going to look on my sum identity for what happens when I add tangent. So I look here. So my sum for tangent, it says tangent of alpha plus beta is the tangent of the first angle plus the tangent of the second angle minus the tangent of the first angle times the tangent of the second angle. But now alpha and beta are all the same angles. They're all x. So that is going to equal tangent x plus tangent x over 1 minus tangent x tangent x. Tangent x plus tangent x is 2 tangent x. Tangent x times tangent x is tangent squared x. That's it. So what did I do to get from here to here? I added in the numerator, right? And then I multiplied in the denominator. All right, any questions so far? Type in the chat if there is anything that I've written and you don't know where it came from or how I got from one step to another. If you're all good, would you type all good in the chat? Gotta know you're out there, people. Alright, all good, all good, all good, all good. I'm all good. Alrighty. So, these are now here. We've proven them. Okay? They're here on our formula chart. So for today, this is our focus. Alright, we're focusing right here on the double angles. So see what we have? Here's our sine, right? And then do you see the cosine has 3 different versions? Right? 3 different versions for cosine, and then there's the tangent. So that's what we just did, encapsulated in our formula chart. Now, what we want to be able to do is, just like we did with our other identities, we want to be able to simplify expressions. We want to be able to find exact values. We want to be able to solve equations. We want to be able to verify identities. So we're going to go through an example of each, and then you're going to try each. Okay? So, all right, so the first skill that we're going to work on is simplify. Alright, so there is our expression, cosine squared 4 theta minus sine squared 4 theta. And so when we're simplifying, we want to see, can we use an identity, right? And we are focused on double angles today. That's going to be our main identities. So if we look at our double angles, does what we have in that problem look sort of like one of these? So I'm going to write over here on the side because, okay, this is another thing, guys. As I keep checking your quizzes and your other assessments, some of you are simplifying things, and you're doing this thing where you draw arrows and you go over here and over there, and some of you it's very logical, but we want to go vertically so that everything we write is congruent, is equal to the thing above it, and we tell a little math story sentence by sentence by sentence, and then anything else we want to write we put over here on the side. So I'm going to write down this double angle identity. Cosine 2 theta equals cosine squared theta minus sine squared theta. Right? This is the identity. Double angle identity. Right? Straight from my formula chart. So, this is a true fact. I don't want to come put it over here. Right? So do you see that what I have is I have cosine squared of an angle minus sine squared of that same angle. But instead of my angle being named theta, my angle is 4 theta. Right? Does everybody see how this is this right-hand side, except that theta is 4 theta? So I'm going to use the double angle identity, and I'm going to replace this right side with the left side here. So this is going to be the cosine of 2, right, because that's what this identity says, times my angle. Well, my angle is 4 theta. And so how did I go from here to here? I did a double angle identity substitution. Double angle identity. Substituted the right side for the left side. Now I just multiply. 4 times 2 is 8. So that's the cosine of 8 theta. Done. Alright, let's do a second one on simplifying. Let's take 6 sine x cosine x. So again, our lesson today is on double angles. So look at your formula chart under double angles. What does that look most like? Do you see that it looks like this, mostly? Alright, so I'm going to write this one over on the side. Just, again, this is on the sideline. I don't put that into my problem. And I don't even have to write it down. But I know some of you are like, Ms. Collier, where did you get that from? So this is my where did you get that from little box. Right? This is a double angle identity. So I sort of have 2 sine theta cosine theta, but not really because I have a 6. But can 6 be factored? Right? Can I take 6 and factor it into 3 times 2 times sine x cosine x? Right? All I did there was factor the number 6 into 3 times 2. Alright, so now does this look exactly like this, with the exception of it's an x instead of a theta? So now I'm going to substitute the left-hand side. So it's going to be sine of 2x. Done. All right, let's do one where we find the exact value. All right, so to find the exact value, you know somewhere in here we're going to be using our unit circle, our standard angles. All right, so I have cosine squared of 5 pi over 12 minus sine squared of 5 pi over 12. And to reiterate my main idea, I cannot, if I just type this into my calculator, I will not get an exact value because I will get a decimal that the calculator has rounded, because 5 pi over 12 is not a standard angle. Right? So I'm not going to get an exact value if I just rely on my calculator. Alright, so cosine squared of an angle minus sine squared of an angle. Look on your double angle section. Do you see that? Is it on a cosine or a sine? You see that it's there under cosine 2 theta? Are we all seeing this right here? So according to that double angle identity, this is going to be the cosine of 2 times my angle, which is 5 pi over 12. Alright, so let's take a break again from our main flow and come over here on the sideline. Just multiplying fractions. Some of you are still having a few issues. So, way number 1, multiplying fractions, that's no problem. Top times top, bottom times bottom, and then simplify. Or way number 2 is this. Simplify first. 2 divided by 2 is 1, and 12 divided by 2 is 6. Now, top times top, bottom times bottom. So when you come in here and you slash that and put a 1 and slash that and put a 6, you are dividing by 2, which is the same thing you got over here when you simplified. Doing this can sometimes save you some work because you'll make your factors much smaller in the first place, right? But the process is the same. You're multiplying the numerators, you're multiplying the denominators, and you are simplifying by a common factor. It's just the order that differs. So this then becomes the cosine of 5 pi over 6. 5 pi over 6 is a standard angle on our unit circle. 5 pi over 6 is in the second quadrant, and we know that the cosine in the second quadrant is negative. And if you have memorized your unit circle, it's negative square root of 3 over 2. And if you have not, you will go to the unit circle, and you will find 5 pi over 6, and you at least know that the cosine is the x value, and there it is, negative square root of 3 over 2. So that is finding the exact value. All right, now we're going to do one that says verify. You might also see the word prove as the instructions here. Verify or prove. Alright, so we have 1 minus cosine of 2 theta over sine of theta times sine of 2 theta equals secant of theta. Okay. When we are doing a verification or a proof, we only write on one side of the equation. Here's the thing. We don't know if this is true, right? We're trying to prove that it's true. If we start doing things to both sides of the equation, then we are assuming it to be true. And you can't assume it to be true. That's what we're trying to prove. So you cannot work across the two sides of the equation. Now, this one looks the most complicated, so it's best to work on this left side and try and make the left side come down to equal the right side. But in our brain, we do want to think, so I'm not going to write it here. I'm going to write it over here on the sideline, that secant theta is equal to 1 over cosine theta. No. Yes. So probably what I'm thinking is I'm going to do a bunch of steps, and I'm going to get to 1 over cosine theta, and then I'm going to get to secant theta. Like, this is probably going to be my second to last step, and then my last step. So I'm thinking that I need to get somehow to 1 over cosine theta. So that's in the back of my mind. So I've got sine theta over sine 2 theta. All right, let's deal with this sine 2 theta first, because with sine, there's only one choice. So I'm going to write down my sine theta. All right. Then I'm going to my formula chart. Okay? Sine of 2 theta is 2 sine theta cosine theta. So I'm going to do a substitution there. So if it helps you guys, I think it is helping some of you anyway, to track with color coding. I'm taking sine theta and I'm substituting it there, right? That's my double angle. That's my double angle identity for sine. That's what I substituted. That part stayed the same. Now, when it comes to cosine of 2 theta, right? I've got choices. So cosine 2 theta, I could use cosine squared theta minus sine squared theta. Or I could do 2 cosine squared theta minus 1. Or I could do 1 minus 2 sine squared theta. Now guys, I could put any one of these in there and eventually get to my answer. But I can also look at what I have and make a pretty good choice. So cosine squared minus sine squared, right? That's going to give me like 2 things in my numerator. Yeah, I'm not seeing that's going to be helpful. Remember, I'm trying to get to 1 over cosine. So if I'm trying to get to 1 over cosine, don't you think I'm going to want to divide some signs? So kind of if you're thinking ahead to where you're going, then it might become kind of obvious to you that if we use this one with the 1 minus 2 sine squared theta, it's going to be the most direct. Alright, so I'm going to replace 1 minus, remember whenever you subtract, put it in parentheses, you're subtracting the whole amount. 1 minus 2 sine squared theta. So I did another substitution. I substituted 1 minus 2 sine squared theta for cosine 2 theta. That was also a double angle identity. Again, I had 3 substitutions to choose from. I chose this one because I'm thinking ahead. I want to get to 1 over cosine. So if I want to get to a 1 in the numerator, and I've got some signs on the bottom to get rid of, that's why I chose that one. Alright, so now let me just do my subtraction. 1 minus 1 is 0, and then minus a negative becomes positive 2 sine squared theta. So what did I do here? I just flat out subtracted. And then I'm just going to rearrange this and multiply, and that'll be 2 sine squared theta cosine theta. So what did I do? I just multiplied. Two divided by 2 is 1. Sine squared theta divided by sine squared theta is 1. 1 times 1 is 1. 1 times 1 is 1, and 1 times cosine theta is cosine theta. It's very important that you understand that these are dividing out to 1. Otherwise, if you just think they're canceling, you might think that that all canceled and that would just be a 0, right? I mean, if it's canceled, it's gone. It's not canceled. It divided to make 1. So what's your numerator? Your numerator is 1. And then 1 over cosine theta is secant theta. Secant theta is secant theta. And I thought I'd show you guys something because I think some of you will find it very interesting. A lot of times what we write in math at the end of this is we write QED. Why in the world would we write QED? Okay, where did I write that down? I want to be able to spell it right. Oh, there it is. This is Latin, and it stands for, I don't know if I'm going to pronounce the Latin right. Y'all feel free to correct me. Quod erat demonstratum. So that's your QED. And loosely translated, it means that which was to be demonstrated. So we were to demonstrate that 1 minus cosine 2 theta over sine theta sine 2 theta equals secant theta. So when we get down to secant theta, QED, that which was to be demonstrated. basically you do all this and it's like mic dropped, there it is. You wanted me to get to secant theta? Ta-da! I got to secant theta. QED, Latin. Alright, last thing we're going to do is we're going to solve some trig equations that have double angles in them. Okay? So, I'm about to move this. I hope you're all done copying. There will be a video if you need to go back and fill things in. Alright, so now let's talk about solve. And we are going to solve on the interval 0 to 2 pi. So we're only looking for a finite number of solutions. Alright, so let's start with this problem. Sine 2x times sine of x equals cosine of x. So remember, when we're solving, we're trying to get down to one trig identity with one angle. You see here I've got 2x for my angle, and here I just have x for my angle. And here I have x for my angle. So I really don't want to have sine of 2x anymore. So the first thing I'm going to do is replace that sine of 2x with my double angle identity. So this is going to be 2 sine x cosine x times sine x equals cosine x. So wait a minute, Miss Collier, what did you do? I took sine of 2x, this part right here, and I substituted it with this double angle identity. Double angle identity. Did a substitution. Now, I could multiply that and get sine squared x, but where's that going to lead me? I don't know. Solving. Now remember, can I divide both sides by cosine x? No. Right? Do you remember why we can't divide by cosine x? We can never ever divide by 0. Cosine x is sometimes 0. So we're not going to divide. Right? It's not going to help us. But what if we subtracted the cosine x so that we equaled 0 and tried to factor? Yeah, that's usually a good idea. So let's do that. 2 sine, I'm going to go ahead and write that as sine squared x cosine x minus cosine x equals 0. Set equal to 0. Setting equal to 0 is a good thing because it allows us to factor. Right? So, look at your two terms. What do they have in common? See the cosine x? See the cosine x? We're going to factor out the cosine x. So once you have two factors being multiplied and equaling 0, that's beautiful. That's beautiful because that then means one of your two factors equals 0. So cosine of x equals 0, or 2 sine squared x minus 1 equals 0. So when is the cosine 0? Remember, cosine is your x value. So your x value is 0 at pi over 2 and down at 3 pi over 2. Alright, now we got to work with this guy. So I'm going to add 1 to both sides. Then I'm going to divide both sides by 2. And then to undo a square, I'm going to take the square root of both sides. That means plus or minus the square root of 1 over 2, which that's plus or minus the square root of 1 over the square root of 2, and the square root of 1 is 1. But 1 over the square root of 2, when I rationalize the denominator, that's the square root of 2 over 2, right? Plus or minus. So right here again, rationalize the denominator. And I know there are some of you out there who are like, I am following everything until we get to those square roots, and I just don't know that part. Okay, perhaps Khan Academy, search rationalize the denominator. I mean, if you're good to here, but you can't make the jump over here, this is not really a trig skill, right? This is just an algebra 2 skill of rationalizing the denominator. So where is it that the sign is positive square root of 2? All right, so remember, sine is positive in your first and second quadrants. So that's pi over 4 and 3 pi over 4. And then when is sine negative square root of 2? Well, that's down in your third and fourth quadrant, 5 pi over 4 and 7 pi over 4. So these are all your solutions. All right, we're going to do one more solving problem together. All right, we have sine of 2x plus cosine of 2x squared equals 1. Now, your first thought might be to do some substitutions here and then simplify before you square. And that is one route that you could take. That actually gets a little messy. You got like a lot of things once you start squaring. So I'm going to suggest that we do the squaring first. So remember that when you have a plus b squared, that's a plus b multiplied by a plus b, and it's going to be a squared plus 2ab plus b squared, right? A times a is a squared, a times b is ab, and b times a is ab, so you always have two of those, and then b times b is b squared. So let's apply that idea here. We would have sine squared of 2x, that's my a squared, plus 2 of sine 2x cosine 2x, plus cosine squared 2x equals 1. And you could stare at this for a long time and think it's a big giant mess. But look for a Pythagorean identity in here. So again, over to the side, I'm not going to write this as part of my thing, but isn't it true that sine squared x plus cosine squared x equals 1? Right? That's a Pythagorean identity. So wouldn't sine squared 2x plus cosine squared 2x just equal 1? So I have 2 sine 2x, cosine 2x plus 1 equals 1. Because of this Pythagorean identity right here. Alright, now I can subtract 1 from both sides. And I'm also going to, well, let me subtract 1 from both sides. 2 sine 2x cosine 2x equals 0. Can divide both sides by 2. So sine 2x cosine 2x equals 0. Now, there's a couple of different ways you could proceed from this point. I'm just going to go ahead and break these down. Sine 2x equals 0. Cosine 2x equals 0. Alright, I'm going to deal with this, with the sine first. So when is sine equal to 0? You see that sine is equal to 0 at 0, right? So 2 times 0, 0. And then sine is also equal to 0 at pi. So I need 2x to equal pi, right? I need this angle to equal pi. So if 2x equals pi, then x is going to equal pi over 2. Let me say that part one more time. Sine of pi is 0. So 2x has to equal pi. So then x is pi over 2. I'm not saying that the sine is 0 at pi over 2. That's not true. But when x is pi over 2, this will be the sine of pi, and the sine of pi is 0. Alright, so let's think about when is the cosine of 2x equal to 0. Well, that's going to happen whenever cosine is pi over 2. So 2x has to equal pi over 2, or 2x has to equal 3 pi over 2. Right, because I'm talking about this angle right here. So then x would equal pi over 4. X would equal 3 pi over 4. But that's not all. So remember when we wanted to find all our angles, we would say pi over 4 plus the period, right? So if I have cosine 2x, what's the period of cosine 2x? The period of regular cosine is 2 pi divided by 2. So the period of cosine 2x is pi. So if I have pi over 4 and I add pi, am I still within 0 to 2 pi? Right? Because I'm not looking for all the answers on the whole domain, but I'm looking for all the answers on one revolution of the unit circle. So pi over 4 plus pi, isn't that 5 pi over 4? And that is still in my interval 0 to 2 pi. And then if I have 3 pi over 4 and I add another pi, I'd be at 7 pi over 4. And I'm still in 1 revolution of my unit circle. Now, if I come back over here to pi over 4 and I add 2 pi, well, now I'm outside my interval. So this is all of them right here.